Our second speaker today is Mariel Supina from the University of California, Berkeley. She will talk about the Equivariant Ehrhart theory of the permutahedron. Please, Mariel.
Yeah, thank you very much for the opportunity to share our research. So I'll be talking about the Equivariant Ehrhart theory of the permutahedron. And this is joint work with Federico Ardila and Andres Vindas-Melendez. And you can find our newly revised preprint on the archive. So to start, I want to talk about standard Ehrhart theory, which is the study of counting lattice points in polytopes. So to start, we start with a d-dimensional integer polytope P with integer vertices. And then we define this function that I'll call L sub P of T, which is the lattice point enumerator. And this takes in a positive integer T, and it outputs the number of integer points inside of the dilation TP. So, and then Ehrhart's theorem says that this lattice point enumerator agrees with a polynomial of degree D. So at the bottom of this slide, you can see if we let P be the unit square, then you can kind of look at or count the number of points in P, 2P, 3P, and you can see that what the pattern is, and you can see that the lattice point enumerator here should be T plus 1 squared. And then the next thing we can do is construct what we call the Ehrhart series, which is the power series where the coefficient of z to the t is the lattice point enumerator evaluated at t. And this has a very nice rational form where the denominator is 1 minus c to the dimension plus 1. And the numerator is this polynomial of degree at most d that we call the h star polynomial of p. So in this example, the h star polynomial will end up being 1 plus c. So then in equivariant Ehrhart theory, which was introduced by Stapledon in 2011, the main idea is that we want to generalize Ehrhart theory to also record information about the symmetries of P. So there's some representation theory going on in the background here, and I'll talk about that a little bit later. But for now, I'm going to give kind of an overview of the combinatorics of what's going on, and then I'll work through the example of the permutahedron, which is what we do in our paper. And then at the end, I'll explain how that ties back into this framework of equivariant Ehrhart theory. So again, we start with a d-dimensional lattice polytope P, and now we also have some group of symmetries G that's acting on P. So then for each element of that symmetry group, we can look at the fixed polytope, which we denote P superscript G. And this is going to be the polytope of points inside of P that are fixed by the action of that group element. And this is now no longer necessarily a lattice polytope, but it is necessarily a rational polytope. And so we no longer have necessarily an Ehrhart polynomial, but we do have an Ehrhart quasi-polynomial, which has this form. So it's a periodic function, and each of these FIs here is a polynomial, and the period has to divide the denominator of the rational vertices of the rational polytope. So this is the case for rational polytopes in general, and in particular for these fixed polytopes of P. So then the idea is that we can, again, construct the Ehrhart series just like before, and we can find its rational form, and we can find an analog to this h star polynomial, except now we find it as a function of the group element. So I'll sort of illustrate this with the example of the permutahedron. So throughout this talk, when I talk about the n permutahedron, I mean the convex hull of all permutations of the coordinates of the point 1, 2, 3, ... up to n. And so here I've pictured the 3 permutahedron and the 4 permutahedron. So notice that how I defined it, it's going to be n-1 dimensional. And there's a lot of really nice ways to describe the permutahedron, but the nicest one for doing Ehrhart theory is the Zona-tope description, which means writing it as a Minkowski sum of line segments. So in the case of the permutahedron pi n is the Zona-tope of the line segments connecting ei to ej for each pair of basis vectors I and j. And Minkowski sum just means that a point in the permutahedron can be obtained as a sum of one point from each of these line segments. And then also the way I defined it, you have to shift it by the all ones vector also. So next we want to look at the fixed polytopes of the permutahedron. So in this case, our acting group will be the symmetric group, which acts on Rn by permuting coordinates of points. And you can see by how we define the permutahedron that it should be invariant under this action of Sn. So then for each sigma in Sn, we can look at the polytope of points in the permutahedron that are fixed, which we call pi n sigma. So in this example, here I'm looking at pi 4, and my sigma is the transposition flipping 1 and 2. And so we get the fixed polytope by intersecting pi 4 with the hyperplane x1 equals x2. And it, not at all coincidentally, it looks like the 3 permutahedron, but it's not the same as that, but combinatorially, it's the same as a 3 permutahedron. So in some work that was presented at last year's FIPSAC, Ardila, Schindler, and Venus-Melendez, they came up with a zonotope description for these fixed polytopes of the permutahedron, and they also computed their volumes. So, okay, so if we have a sigma in Sn, I'll always, throughout this talk, I'll call the number of cycles of sigma, I'll call that m, and I'll label the cycles sigma 1 through sigma m, and their lengths will be L1 through Lm. So then with that notation, the fixed polytope pi n sigma has this zonotope description where it's the Minkowski sum of the line segments connecting Lj times E sigma k to Lk times E sigma j for all pairs of cycles sigma j and sigma k. And here E sigma k is just going to be the sum of the EIs where I is an element of the cycle sigma k. And then very importantly, so far that was a lattice zonotope, but very importantly, there's this rational shift also that happens where we shift it by the sum of Lk plus 1 over 2 times E sigma k. So notice here that if all of the cycles have odd length, then this will actually be an integer shift and this will be an integer zonotope. But if any of the cycles of sigma have even length, then this is in a rational shift. But it's only half integral, the denominator is 2, so it's not so bad. So down at the bottom there is the zonotope description of that hexagon fixed polytope from the previous slide, and you can see that it's rational because of the cycle 1, 2 of length 2. Okay, so the reason why zonotope descriptions are really nice for doing Ehrhart theory is that zonotopes can be naturally tiled by half-open parallelotopes. And the way that this works is you look at the collection of line segments generating your zonotope, and you look at all the vectors, the direction vectors of those line segments, and then you have exactly one tiling or exactly one tile in your tiling for each linearly independent subset of the generators. So here this is a picture of the 3 permutahedron and it's one of its tilings. And so you can see that for each pair of EI minus EJs, we can get a 2-dimensional tile in the tiling, and then for each one-dimensional, or for each linearly independent subset of dimension of size 1, we get a line segment, and then for the empty set, we get the point in the middle. So the reason why this is nice for doing Ehrhart theory is Stanley's theorem, which says that all we need to do is decompose our zonotope by this tiling and then count the number of lattice points inside of each tile, which is not hard to do. The Ehrhart polynomial of your zonotope will be the sum over the linearly independent subsets of the generators, and then for each subset you take the volume of the relative volume of the parallelotope generated by that subset, and that volume will be so first of all, that volume is easy to compute. It's just an easy determinant because it's a parallelotope, and it's also the same as the number of lattice points in that tile. And then we have to multiply that by t to the dimension of the tile. So in this case, for the hexagon, you can see that all of these tiles have relative volume 1. And so the 3 top dimensional tiles will contribute t squared to the Ehrhart polynomial. The line segments will contribute t, and the point contributes 1, and we get that the Ehrhart polynomial is 3t squared plus 3t plus 1. So in the case of the fixed polytopes of the permutahedron, we actually have a rational translate of a lattice zonotope. So we need to figure out how we can adapt this process for that case. So when we have a rational translate of a lattice zonotope, it still decomposes into parallelotopes in the same way. It's just that now not all of them necessarily intersect the lattice. So in this example, I shifted the hexagon like half a unit south, and now these 2 lower line segments don't have any lattice points, and neither does the point in the middle. And also notice that if you take the whole affine span of one of these lower line segments, it creates a whole line that doesn't intersect the lattice at all. So our question becomes, 1, how can we count the linearly independent subsets of the generators of the fixed polytope? And 2, how can we check which of these subsets correspond to tiles that actually intersect the lattice? So we did this for the fixed polytopes. So the generating set of the zonotope is these Li e sigma j minus Lj e sigma i's, where remember we have one of these for each pair of cycles, sigma I and sigma j of sigma. And the linearly independent subsets of this generating set are in bijection with forests on the vertex set M, where M is the number of cycles. And so when we're computing this Ehrhart polynomial, we can actually sum over forests because these correspond to linearly independent sets. And in fact, to check whether a tile contains any lattice points, we don't actually need to know about the edges of its corresponding forest. We only care about the underlying set partition of the vertex set into connected components. And so I'll label set partitions of the vertex set, I'll call those pi. So if all of the cycles are odd length, remember, then we have a lattice fixed polytope, and we can just directly use Stanley's formula to compute the Ehrhart polynomial by summing over linearly independent sets, which are forests, and we can sort of condense that but to sum over, to like group it by set partitions of the vertex set. And this v pi here is an easy to compute coefficient, which I'll show the formula for later. But then if some of the cycles are even length, then we have a half integral fixed polytope. And so we need to figure out, we don't want to sum over all of the set partitions, just the ones corresponding to tiles that have lattice points. So we were able to characterize which set partitions correspond to these tiles by introducing this concept of lambda compatibility. So here lambda is just the cycle type of sigma. So it's the partition L1 through Lm given by the cycle lengths of the cycles of sigma. And we say that a set partition of the set M, which remember is the number of cycles, we say that it's lambda compatible if for each block in the set partition, either you have Lj odd for some j in that block, or the minimum 2 valuation among the cycle lengths Lj for j in that block is attained an even number of times. And so this kind of surprising number theoretic condition came from the fact that we're actually looking at the whole span of the tile, and we're trying to see whether the whole affine span contains lattice points. And this amounts to solving or checking if a system of linear equations has any integer solutions. And so that's where we get this number theoretic condition from. And so we found that if the tile corresponds to a forest whose underlying set partition is lambda compatible, it contains its volume number of lattice points, and otherwise it contains 0 lattice points. And so this let us compute the Ehrhart quasi-polynomial for the fixed polytope. So for even dilations, we just sum over all of the set partitions of the set M. And for odd dilations, we only want to sum over the lambda compatible set partitions. And then here, this coefficient b pi is given by this formula. So now that we have the Ehrhart quasi-polynomial, we can also compute the Ehrhart series of the fixed polytope by constructing the series where the coefficient of z to the t is the quasi-polynomial evaluated at t. And we found that it has this rational form that's displayed here. So here it's displayed as a sum of rational functions. And the important thing about this is that later, in order to check one of Stapledon's conjectures in the case of the permutahedron, we will need to analyze the poles of this rational function. So that's where this will come into play later. So that's the combinatorial side of what we did. So now I want to tell you more about like what's actually going on in the background with the equivariant Ehrhart theory. So going back to the general case, remember we have some polytope P and we have some group G that's acting on P. So we're going to call the d-dimensional representation of G induced by its action on P, we'll call that rho. So in our example, P was the permutahedron, G was the symmetric group, and this representation rho will be the standard representation of the symmetric group, which is acting on Rn by permuting coordinates of points, but then we kind of quotient out by the all ones, the span of the all ones vector, which is the fixed subspace. Okay, and then the analog of the Ehrhart polynomial in classical Ehrhart theory here is going to be a family of permutation characters, which we call chi sub tp. So we have one of these for each positive integer t. And the way that this goes is that for each positive integer t, we can take the dilation tp of p, and we can look at the set of lattice points inside of that dilation. And now G will act on this polytope TP, and it'll permute the set of lattice points amongst themselves. So what we can do is we can construct a vector space where we have one basis vector for each lattice point in TP, and then we can get an action on that vector space, a G action on that vector space by how G permutes the lattice points inside of TP. And so this gives you a representation of G. And chi sub tp will be the character of this representation. So, the key thing to know about this is that a character is going to be a function on the elements of the group. And if you plug in some element of the group, G, to your character chi sub tp, what you're going to get is the number of basis vectors in that vector space we just constructed that are fixed by the action of that element. And in this case, that's the number of lattice points inside of TP that are fixed by the action of that element, which is the same as taking the lattice point enumerator of the fixed polytope fixed by that element and plugging in T to that. So this is how this character relates to the Ehrhart polynomial of the polytope. And then, just like before, we can construct this equivariant Ehrhart series where the coefficients now, instead of being integers, are characters, chi sub tp. And this, Stapledon showed that this has a nice rational form where the denominator is 1 minus z times the determinant of the identity minus rho times z. And the numerator is this series that we call the H star series. And this is a series whose coefficients are virtual characters, which means they can be positive and negative linear combinations of characters of G. And just because of what I said before about evaluating the characters at an element of the group, if we evaluate this equivariant Ehrhart series at some element of the group, what we'll get is the Ehrhart series of the fixed polytope of P fixed by that element of the group. So the idea of equivariant Ehrhart theory, or the sort of open questions in equivariant Ehrhart theory, are about this H star series. And Stapledon had a big conjecture about this. So first of all, we call the series effective if all of the coefficients are characters. So they're positive combinations of characters of G. And then Stapledon conjectured that these three conditions are equivalent, that H star is actually a polynomial, that it's effective, and that the toric variety of P admits a G-invariant non-degenerate hypersurface. And he showed that kind of the upward direction of implications holds, so only the downward direction is conjectured. And actually, so after we did this project and we put our paper on the archive, we found out that, so in an email from 2013, Paco Santos and Alan Stapledon actually constructed a counterexample to 1 implies 3. So as stated, this conjecture doesn't hold, but there's still a lot of interesting questions here. We can ask, are 1 and 2 equivalent? We could also ask, how can we reformulate 3 to make this true, or under what conditions is the whole conjecture true? But when we were doing our project, we didn't know about this, and so we wanted to check whether this conjecture held for the permutahedron. So going back to the special case of the permutahedron, here the representation is the standard representation of Sn, and the denominator of this, the equivariant Ehrhart series, has this really nice form, the product of 1 minus z to the cycle lengths of sigma. So we wanted to check whether the H star series is a polynomial. So we wanted to check for each sigma. We wanted to find out what the H star series was evaluated at that sigma. And so the way to do that is take this nice denominator, the product of 1 minus z to the cycle lengths, and multiply by that formula for the Ehrhart series of the fixed polytope, which was that big sum of rational functions from before. And then this will be a polynomial evaluated at that sigma whenever the zeros of this product of 1 minus z to the cycle lengths cancel with the poles of the Ehrhart series of the fixed polytope. So it turns out that, so in order for the H star series to be polynomial, it needs to be polynomial evaluated at every sigma in Sn. And it turns out that this only happens when n is less than or equal to 3. So for the hexagon, the line segment, and the point. And any higher dimensional permutahedron, we found that it's not a polynomial. And then by checking the other conditions in the conjecture, we were able to show that the conjecture holds for all permutahedra. So here's an example. So this is pi3, the hexagon. So in the left column, I have all of the possible cycle types of sigma in S3. In the second column, I have the Ehrhart polynomial, quasi-polynomial of the fixed polytope fixed by that via sigma with that cycle type. In the third column, I have the Ehrhart series of the fixed polytope, and I made it so the denominator is the product of 1 minus z to the cycle lengths. And then by looking at the numerator of that, we can find out what the H star series should be evaluated at a sigma with that cycle type. And we see that here they're all polynomials. And also if we write them out as in terms of the irreducible characters of S3, we find out that all the coefficients are positive combinations of these, and so it's effective. And then by doing some other business where we used some previous work on discriminants of symmetric polynomials by Perminov and Shakirov, we were able to also prove that for S3, the toric variety of pi3 admits a G invariant, an S3 invariant non-degenerate hypersurface. So this case satisfies Stapledon's conjecture. So then here's the next case. So this is pi4. So now again, I have the same kind of table, but now I want to draw your attention to the second row. So if sigma has cycle type 2, 1, 1, for example, that transposition 1, 2 that I showed the picture of way at the beginning of my talk, then we see that in the Ehrhart series of the fixed polytope, we actually get some factors in the denominator that don't come from the product of 1 minus z to the cycle lengths. And so we have to think of these factors as part of the numerator, part of the H star series. And so that's why evaluated at a sigma with that cycle type, the H star series is not a polynomial. And so we get, for this case, H star is not a polynomial. And then if you look at this at the bottom, the writing it out in terms of the irreducible characters of S4, we can see that it's not effective because there's some negative signs in front of some of the characters. And then it's also pretty easy to see that for this permutahedron and higher dimensional permutahedra, it also fails the SN invariant non-degenerate hypersurface condition. So Stapledon's conjecture also holds in this case in that all of the conditions are false. So for some future directions, the overall goal is to reformulate the effectiveness conjecture. So an easy starting point, because we relied so heavily on the zonotope composition of the permutahedron, a good starting point might be to do this for other zonotopes. So I've been working on this a bit for graphic zonotopes, and I also know that Ardila, Beck, and McWhorter had a recent paper where they made some progress toward doing this for Coxeter permutahedra. We can also check about other SN invariant polytopes. I started thinking about this a little bit. I had some ideas about the hypersurface property, but it ended up being more complicated than I had thought. So that's something I'm interested in learning more about. And then another place that we could start could be hypersimplices under the action of the cyclic group, because at last year's FIPSAC, Donghyun Kim presented his work where he showed that the coefficients of the H star polynomial of hypersimplices count these combinatorial objects that have a natural Z mod and Z action. So, so that could be a direction for doing this as well. So that's all that I have today, and these are all of my references. Thank you.
Thanks, Mariel. We'll take some time to unshare your screen. Yeah, we can all share our reactions. I see some questions in the chat, so I'll pass it to Harvind.
Okay, thanks. Nice talk. So Vic Reiner was asking a question, but I suppose this is related to your last slide, but I'll ask it anyway. He says, are permutahedra Z mod NZ effective even though they fail to be Sn effective beyond n equals 3? For example, is there a version of Nick Early's hypersimplex conjecture for them, the one proven by Donghyun Kim? I suppose that's what you mentioned. Do their toric varieties have an explicit Z mod NZ invariant non-degenerate hypersurface?
Yeah, I haven't, that's a really good question, and I would have to think about it a bit in order to answer that right now. But yeah, that's a good question that we could ask. So.
Okay, thank you. Jia Yuan Wang asks, for any G in Sn, is the quantitative H star 1G a non-negative integer?
Wait, so can you repeat the question?
So he asks, for any G in Sn, is the quantitative, I suppose he means quantity, is the quantity H star bracket 1 of G a non-negative integer?
Yeah, shoot, so we did, I remember that we did like Stapledon had a conjecture about this and we checked it and it held for the permutahedron, but I don't remember, like, I wouldn't be able to answer off the top of my head if this is the if this is what the conjecture states, but I could easily check that. Yeah, and that would also be in our paper, I think. So
okay, thank you. Bruce Sagan asks, even though all H star Z of sigma are not polynomials for n at least 4, can you characterize those which are?
Yeah. So it turned out to be that it was a polynomial if the number of let me share my slides one more time.
Mm-hmm.
I think I'm doing it. So let me go back to the, yeah. So it's a polynomial if the number of odd parts of the cycle type is 0, 1, or all of them, I believe. And so that's why it fails for S4, because you have this cycle type, this partition that has, oh no, yeah, okay, yeah. You have this partition that has 2 odd parts, which is not 0, 1, or all of them. And so you can, the reason it fails is that for higher dimensional Sn, and for higher n, you always have some partition that fails this. But if you took a subgroup of Sn where all of the cycle types did satisfy this condition, then it would be a polynomial. Yeah.
Okay. Nice, thank you. I think Alejandro asked essentially the same question. Are there any more questions? We have a minute. I'm trying to see if anybody has raised their hands. No? Okay, over to you, Angela.
Okay, so let's thank Mariel again.